Welcome to part 3 of our first test review. I have here the distribution of ACT scores for high school students in the United States is normally distributed. Normally distributed, what does that mean? That means it's bell-shaped. With a mean of 15, standard deviation of 4. And for parts A, B, and C, we want to find the range of AT scores within 1 standard deviation of the mean, 2 standard deviations of the mean, and 3 standard deviations of the mean, respectively. Since it's bell-shaped, that normal distribution, all 3 of these use the empirical rule. So I'll put an E here on the side, just to make note of that. So for the 1 standard deviation of the mean, we're adding and subtracting 1 standard deviation. This will be 15 plus or minus 4. So subtracting, we get 11. And adding, we get 19. And the percentage, according to the empirical rule for this, is approximately 68% of ACT scores will be between 11 and 19. Part B wanted the 2 standard deviations. So the mean plus or minus 2 standard deviations. 15 plus or minus 2 times 4, or 8. So this would be, for this case, 7 to 23. So 2 standard deviations, this would be approximately 95% of ACT scores will be between 7 and 23. And then finally, part C wants the 3 standard deviations about the mean. So mean plus or minus 3 standard deviations. So 15 plus and minus, plus and minus. There we go. 15 plus and minus 3 times 4. So we're adding and subtracting 12. This is going to make 3 to 27. And based on the 3 standard deviations, this would be approximately 99.7% of ACT scores will be between 3 and 27. All right, we still have 2 more parts to this question, right? But those 3 specifically dealt with the empirical rule. Part D has at least what percentage of ACT scores for high school students are between 3 and 27. Likewise, part E has at least what percentage of ACT scores for high school students are within 1.5 standard deviations of the mean. Because of that lovely phrase, at least, at least, at least. This uses the Chebyshev's inequality. So even though it's it's a bell-shaped distribution, these ones need to use the Chebyshev inequality. So in our case, we would need to know how many times we would need to add or subtract the standard deviation from the mean to get 3 and 27. I mean, from part C above, we already know that answer, but just to make note of the step again, this would be 15 plus some number times 4 is equal to 27, for example. And based on part C, we know K in this case would be 3, right? We had 12 to 15 to get 27. So to get that 12, K would be 3. And using Chebyshev's inequality, this will be 1 minus 1 over 3 which is okay, squared times 100%. So 1 minus 1/9 times 100%. So 1/9, that's 0.11111 repeating. So 1 minus that times 100%. This will make 89.9999 repeating percent. Since I want it round to the whole number, this would round to about 90%. So at least 90% of ACT scores will be between 3 and 27. And then for the 1.5 standard deviations of the mean, this would be 1 minus 1 over 1.5 squared times 100%. That makes, rounding this time to 2 decimals, 55.56%. Once you toss that expression into a calculator. To get the range of values, this would be 15 plus or minus 1.5 times 4. So we're adding and subtracting, in this case, 6. So subtracting makes 9, and adding makes 21. So at least 55.56% of ACT scores will be between 9 and 21. Number 8, I gave a graph, which shows the median earnings for females from 2005 to 2009 and constant $2009. And we want to know, what impression is this graph trying to display, right? Let's look at it, yeah? From 2005, we have, an amount less than $35,000. But then by 2009, it jumps up to somewhere between 36,000 and 36,500. But what's trying to show is a giant increase. And I'll put giant in quotation marks since, it's based on those numbers, that is not giant. But a giant increase by 2009 in the median earnings of females and constant $2009. And part B wants to know what's wrong with it, right? So looking at it, we could definitely tell that that y-axis does not start at 0, so it completely messed up that proportionality. So what's wrong with it? The y-axis did not start at 0. And then for question number 9, I have an echinacea tab. There we go. The data set contains whether the subjects became infected based on treatment they received. We have the placebo, 20% extract, and 60% extract. We want a contingency table along with the marginal frequencies. And then we want to rename the tab the echinacea tab table. So let me pull that up here. That being this is the table that's referencing. We are going to select this table. And like before, go to Insert, Pivot Table. I'm going to hit OK. And it's going to give us this. So for the rows, based upon what this table is doing, it is going to be the result. So infected versus not infected. For the columns, that's going to be the treatment group. 20%, 60%, and placebo. And the counts are going to go into the values. And as you can see, we obtain our contingency table, and the marginal frequencies are all given on there in the grand total row and column, respectively. To rename it again, we're going to left, double left click the sheet 2 name on there and rename that the Echinacea table. And insert that on there. Let me know if you have any questions or concerns. Thank you.